Welcome to RTXDI, Details on Achieving Real-Time Performance. I'm Chris Wyman, a Principal Research Scientist at Nvidia. So recently we launched RTX Direct Illumination, also known as RTXDI. You can find more information on our developer web pages here. And the idea of this SDK is it allows you to render millions of dynamic lights with primitives of all different sorts, with or without IES profiles on these lights. You can also have your emissives textured, and the light probe, the environment map, can also emit light as well. So on this slide it compares two images, one with RTXDI on, where all of the lights in the scene, including all the little LEDs and the headlights on this vehicle, cast lighting and shadows throughout the scene. And this is compared with a more traditional approach on the right, where the emissives just glow and don't affect the local environment of the other geometry nearby. So the SDK includes white box source. So if you download the SDK, you'll have access to the source, and this allows you to integrate it flexibly into your game and your engine. The SDK development and sample app has been led by Alexei Panteleev, who's done an amazing job both on the SDK and the sample app that allows you to play with the parameters and see how they affect the results. So please go take a look. But what I want to do today is explore some of the algorithmic details, do a technical deep dive into how we made RTXDI fast. So currently RTXDI is largely based on an algorithm known as RESTIR, or Reservoir Spatiotemporal Importance Resampling. And we presented the basics of RESTIR a number of times last year, including at SIGGRAPH, where it was the research with our collaborators at Dartmouth was first presented, as well as at GTC when we announced RTXDI, and at HPG when we had a talk discussing some of the details of how it works. What I'd like to do today is do a quick high-level review for those of you who may not be familiar with RESTIR, but what I really want to focus in on today is the improvements that we've made since then to achieve real-time performance. So again, I'm going to do an overview. I'm going to talk about memory coherence issues, which were a big performance issue that we had to address, and then I'm going to talk about intelligently refactoring the code. So first, let's start at the basics with physically based rendering. Hopefully, all of you are familiar with this. Physically based rendering is the notion that you'd like to solve the mathematical equations describing how light interacts with the scene. And your renderer may focus on different aspects, some more than others. But typically the idea is that the rendering equation's involved, and you want to integrate this equation here to compute the color at any given pixel. Now, the two hard parts in rasterization are this inside the integral, the term L, which is the incident lighting at any given pixel from a direction. And this is just difficult to compute in raster because you don't know that. You're processing one triangle at a time. And the second hard part is actually the integral itself, because you need to integrate the illumination over the entire hemisphere at every point. Moving to ray tracing, this changes a little bit. In DXR and other ray tracing IPAs, it's simple to just call trace ray to compute the light in any arbitrary direction. However, it doesn't actually make the integration any easier. You still need to integrate the light coming from the entire hemisphere. So how do you handle these sort of high complexity and tough integrals? Well, typically you do something, like Monte Carlo integration to numerically sample your integral. And of course, you often use this with importance sampling, where Monte Carlo is the numerical sampling of the integral, and importance sampling is to try to minimize the n value here. Let me highlight it there. Try to minimize the n there, and you do this by picking a good distribution p to minimize this n. And an important question for real-time rendering is, can we do perfect importance sampling? Meaning, can we get n down to 1? And in order to do this, what you need to do is you need to have your density function proportional to f. And because the density needs to integrate to 1, you can compute this constant proportionality, and it's this integral here, which unfortunately means that in order to sample the rendering equation, you first need a solution to the rendering equation, which is a little unfortunate. But since we're approximating this, right, this importance sampling is doing an approximation of the integral, there's no reason we have to solve it for real here. We could just approximate the perfect importance sampling. And we do this by replacing this integral here with another Monte Carlo sum. And if you do that and then rearrange the terms, you get this estimator down here, which is known as the resampled importance sampling estimator. And this was introduced by to graphics by Talbot et al. In 2005. So what is this thing? What is this RIS estimator? Let's look at the estimator here a little bit more closely. We need our color at a pixel. So here our color is F, and the integral we're trying to integrate, the rendering equation, I've sort of simplified to represent as F throughout this talk. What we want to do is we want to minimize the number of rays that we need to sample N, and we do that in the RIS estimator by reusing information, beg, borrow, and stealing from our neighbors. So by leveraging the information from our spatial and temporal neighbors, we're able to improve the sampling at the current pixel. Now, an important thing to notice about this estimator is this density P is part of an importance sampling, a Monte Carlo estimate here in this green box. And you might ask, could we do perfect importance sampling there? And of course, again, you can't do perfect importance sampling, but again, you can estimate it using Monte Carlo integration. And so what this means is you can turn this into an indefinite chain of resampling estimators. And that's really what RESTOR is. It allows you to put in an estimate and keep estimating the estimate to improve the quality. And what this allows you to do is to feed samples in from everywhere you can think of: spatial samples, temporal samples, estimate at your current pixel, and maybe other information that you can think of. And you feed these all in, and each new bit of information that you feed in improves the sampling quality. And so you get this RESTOR pipeline down here where you generate some initial light candidates for every pixel. You select the lights from last frame that you thought were good, and you take the lights from your neighboring pixels which were good. You put them all into this mix and apply resampling a couple times, and then finally you shade. So what does this get us? Well, so this is an image from our SIGGRAPH paper last year. This is part of the teaser. And this is a very, very complicated scene with about 3 million lights, emissive triangles. And these are scattered across 5 to 10 different amusement park rides. And many of them are animated and moving around quite a bit. And so there's 3 million emissive triangles, dynamic, and this renders in about 50 milliseconds, which is really quite good, especially compared to state of the art. However, it's not quite game performance. In fact, it's nowhere close. And so one of our key goals with the SDK in RTXDI was to improve the performance of RESTOR so that we could get it down to a performance envelope that you could feasibly consider doing. And so here's the same scene. Over the course of the year, our material model has evolved a little bit, so it looks a little bit different. But here we're rendering these 3 million emissive lights, and the total time for direct lighting here is 4.6 milliseconds. And that includes all of the lights, all of the shadows. All right. So now that we've sort of talked about where we're going, let's talk about some memory coherence issues. And the reason for this is when we did the perf analysis of our research prototype, we found out that memory coherence and bandwidth were really the key bottlenecks in the algorithm. And there's 3 main ways that RESTOR consumes memory. First of all, you have this candidate phase where each pixel selects some number of light samples to inject into this process. Then, because we're doing resampling, we need to recompute samples from prior frames or from adjacent pixels at the current pixel, and that means we need to read gbuffer data multiple times as we're resampling these lights. And then we have reservoirs. These are the intermediate data structures that we use to pass our light samples between different kernels or between different frames. Now, for gbuffers and reservoirs, there's sort of standard ways to improve the coherence the bandwidth and coherence here. And one is we can compress to minimize bandwidth. We can merge kernels to minimize the sort of intermediate read-writes between them. Or we can minimize the size of the reservoir, meaning the number of samples, so that we have less memory to read. These are all fairly standard. They're important, very important. But I'm not going to talk about them much more in this talk. What I want to focus on is the random selection of the lights. And when we first ran this by the perf guys, many of them openly wondered why we designed such an algorithm that randomly selects lights from memory in an incoherent way. So why is sampling lights coherently a problem? What's the problem here? So imagine you have your long list of lights down here that in our amusement park scene might have a list of 3 million different emissives. And what we need to do is we need to select some of them randomly to light our scene. And because we want this to converge to the right answer, we need to have a good chance or an equal chance of sampling lights throughout this scene. And this randomization is required. We have to have some probability to select each of these lights or we won't converge to the right answer. Now, because we're only picking a small number of lights from a very large list, this gives us incoherency. And because each pixel chooses a different random subset, we can thrash our cache fairly badly. So it's interesting that the Reeser algorithm actually requires a constant number of memory lookups. It's very efficient computationally. But when we looked at the performance from scene to scene, we found out that from simple scenes to very complicated ones, our costs could vary by over a factor of 20. And this was largely due to the caching. Some scenes fit in L1, some scenes fit into L2, some scenes you need to go to DRAM for almost every access, and those ones just get horrible performance with the research prototype we had before. So an interesting question is, can we pre-randomize to move this incoherency out of our inner loop? And it turns out that the answer is yes. The key observation that we made, though, is that degenerate RIS steps allow us to reshape this computation. And this is a really interesting observation, I think. So if we go back to this RIS estimator here, what if we let P equal to P hat? What if we let this become degenerate? So if we do that and we write out the estimator, it turns into this thing here, and of course these guys cancel into a 1 and then a sum over m things and divide by 1 or 1 over n, that m also cancels. And so what this turns into here is this is the standard Monte Carlo estimator, but we've computed it in 2 steps. First we pick m samples from the whole universe of all of our lights, and then we pick n samples from that smaller subset. Even though this is a standard, it turns into a standard Monte Carlo estimate, we do it in 2 steps, and that's really key, because these 2 steps can run in 2 separate kernels at 2 different frequencies. So what we actually do is once per frame, we create a set of lights, and these sets of lights contain a small fixed number of light samples from our entire universe. And we create these sets of lights, or these pools of lights, using the same PDFP that we would have used on a per pixel basis before. Then, when we render per pixel, what we do is we randomly pick one of these pools of lights, just one of them, and then that pixel will select m lights from the small pool that we just selected. Now, because the PDFs are the same, it turns out we sample uniformly, although that's not strictly required in a more general version of this. But then once we're done with that, we can continue research as if we had selected those m random candidates from the entire universe of lights. And it just works. It's really great. For further cache improvement, you can actually select your pools of lights not on a per pixel basis, but over some fixed window in screen space. Say every pixel in an 8x8 block could use the same pool of lights for their candidates. Now, this doesn't mean they all will pick the same light, but it does introduce the possibility for more correlations. And so this block size needs to be relatively small, but big enough to unlock further cache improvements. And 8x8 was about the sweet spot. Now, an interesting thing is we found that 128 pools of lights, each with 1,000 lights, worked well across most or all of our scenes, from very simple ones like a Cornell box, up to very complicated ones like the amusement park. An additional advantage of this pre-randomization is it seamlessly handles multiple different light types, for instance, probes, triangles, spheres, capsules, etc. You might ask, why are handling all these different light types difficult? Well, if you have many different lights, in order to pick a light sample, first of all, you need to pick a type of light, say the light probe. Then you need to pick which one of your light probes Then you need to pick a point on that surface. And when you do this for all of your different light types, this leads to execution and data divergence. And this can be really tricky. But by pre-randomizing, we can move this divergence out of the inner loop. And the point is, if you can insert one degenerate RIS step, why not insert 2 or 3 or 4? And so what this means is you could sample into a pool of light samples on a per type basis. Say you get a pool of samples that are all on triangle lights, a different pool with light samples only on spheres. And then once you have all of those different pools, you can resample a second time into the pools we talked about on the last slide. So what does this get us? So going back to the amusement park image that we showed before, in our SIGGRAPH paper last year, it took 50 milliseconds to do the lighting pass, of which 20 milliseconds was for these initial candidates. Today, in my research prototype, which is slightly different than RTXDI, but essentially it's all there, it costs 4.6 milliseconds here, of which 0.8 milliseconds is for the initial light sampling. And this is not only a huge improvement in sort of absolute magnitude, but also a percentage of the frame time. All right, so now that we've talked about the memory issues, let's dive into how we can refactor some of the computations to reduce redundancy and also improve performance. So the first thing I want to talk about is ray count. So our initial research prototype used 5 rays per pixel. And that's a pretty big ask in a time when most games use maybe a quarter or half ray per pixel, or maybe up to 1 in sort of really advanced ones. So 5 is a really big ask. So why did we have 5 rays per pixel? Well, if you go down here to this pipeline, the restore pipeline, what we did is we generated some candidates, we picked one, and then we shot a shadow ray here. And the reason to do this can be seen in this scene up here. This is a fairly simple scene, Soda Hall. There's not interesting materials, but it is a 6-floor building with about 40 rooms per floor and multiple lights in each room. And so in this room here, we might be selecting a light 4 floors up across the building, and that's not really relevant to any of the pixels on our screen. And so by shooting a shadow ray here, we can avoid sharing that data with our neighbors and polluting their pool of lights. And so this one sort of global guide ray really improves the quality that you achieve with Restore. The other 4 shadow rays happen during shading. So you have some candidates you reuse from prior frames and from your neighbor pixel, and from all of these you pick 4 light samples that you want to shade, and you shoot 1 shadow ray for each. Now if you step back a little bit though and look at these 3 images, you might wonder how important are all of these rays, particularly these last 4. Right, this first ray gives a huge quality improvement, but these 4 ones after are much smaller relative magnitude, even though the contact shadows are quite important. It's a smaller magnitude change. So you might ask, what do these rays do? Now remember that these shadow rays are the n in our RIS estimator, right? And what this n does is it controls the variance of this part, the ratio f over p hat. And so you might ask, does n equals 4 really matter here? Do you need n equals 8, or is n equals 1 sufficient? Excuse me. So if you look at these images here, with the bistro with final shadow rays, looks pretty good. Without shadow rays, there's definitely these final shadow rays. There's definitely a loss of quality, and so this is equal. This middle one's using n of 0, really. But the delta between these two is only this thing here. And so n controls the variance that you get over here. And you might ask, do you really need 4 rays per pixel to control the error of something of this magnitude? And what we decided was, let's let the denoiser handle that. We have some pretty good denoisers these days. And on the order of magnitude of this difference image, n equals fine actually, or n equals 1 is actually fine. And this cuts the ray budget down to 2 rays per pixel. Now, there's some other reasons that we did this that's beyond the scope of this talk. but this significantly reduces our cost by reducing our array budget from 5 to 2. Now, if you want to reduce the array budget further, there's standard ways to do this that are very promising and useful. Checkerboarding, lower resolution reservoirs, so rendering the lighting at lower resolution and upscaling. And then there's some additional tricks we're going to talk about later. So let's talk about reusing samples more intelligently. So if we look at the restore pipeline here, it's sort of split into 3 phases. One for the current pixel, one to reuse temporally, one to reuse spatially. When we sat down and looked at this very carefully, though, we found out that the temporal reuse was way more important than spatial reuse. And sort of to exemplify this here, here's the same bistro scene where on the left we're using just the initial candidates. Then we have spatial reuse only here. Then we have temporal reuse only here. And then we have both spatial and temporal reuse on the far right. Now, the thing to notice, which is actually fairly obvious, is there's not a huge difference between temporal reuse and using both spatial and temporal. There's a slight difference, but it's hard to see. And so this made us ask, why use spatial reuse at all? Now, it turns out that spatial reuse actually is important because temporal reuse looks good when you're not moving, but with disocclusions as you move around and issues when you zoom in and out by reprojecting, but back projecting between your prior frame and the current frame, there's some temporal issues that spatial reuse helps dither away. It also helps bring in data from adjacent pixels into disocclusion regions. But we do want to minimize this reuse because this contribution is not as important as the one from temporal. And so we found that exactly one spatial tap seems sufficient, although 2 or 3 can sometimes help with noise. So once we realize this, there's actually some additional opportunities for redundancy reduction. So if we go back to our restore pipeline and look at what's actually getting shaded here, it turns out that only one of 3 light samples ever gets shaded here. There's the winner of our pool of candidates that we generate per pixel. There's the one sample from our prior frame, or there's the one sample from our neighbor pixel. And only one of these 3 shaders or samples is shaded down here. Now we trace 2 shadow rays, one here for our initial candidate, and then one during final shading down here. Now, something you should realize looking at this is there's a reasonable chance these are duplicates. It's not 1 in 3, but it's something like that, roughly 1 in 3 chance that this sample here goes all the way through. And that means you'd shoot the same shadow ray twice. That seems like a waste. Now, additionally, because you're doing temporal reuse, you have some visibility information from last frame. Now, it is approximate because things can change, things can move, and so it's only an approximate visibility, but it's a pretty good approximation. I mean, it's only 15 or 30 milliseconds out of date. And so if you think about that, now there's a really good chance that this guy's redundant. Both of these 2 samples have good visibility information. So maybe you move that visibility ray up here to the only one of the 3 samples that doesn't have any visibility information. And now you're only shooting 2 rays per pixel, but now you could shade all 3. Now, unfortunately, reusing visibility like you do here introduces hard to control bias. And the reason for this is the bias can feed forward in a temporal way and really explode in corner cases where it's bad. But an important thing to realize is there's 2 things going on in this pipeline. There's shading, and the goal of shading is to create the best possible image for the current frame. And then there's feeding forward a sample to next frame. And the goal of that has nothing to do with making a good image this frame. It's all about making a good image next frame. And so why not split these into 2 different pieces? We can decouple the shading and reuse. And when we do that, our approximate visibility is only applied to the shading, not to the reuse, so it never feeds forward in an uncontrollable loop. So that means we have a little bit of bias in our shading, but it's transient, it just lasts 1 frame, and then it goes away. And that's not bad at all. And now we have 3 shades per pixel at the cost of our 2 rays that we had before. Now, another thing to notice is we can be more aggressive and reuse visibility from our neighboring pixel as well. Now, this noticeably lightens shadows, but this degradation is parameterizable. We could only reuse visibility from pixels with a certain radius of ours, and we could shoot rays for things that are further away. But this gives us a tuning knob that allows us to tune down the quality in exchange for higher performance and fewer rays. So what does this get us? Well, this is the Paris Opera House from TurboSquid, which is a really amazing model, about 500,000 emissives. And this is with restir before we decouple shading. Now I'm going to flip to the next slide where I show after we do decoupled shading, and particularly take a look at the black speckles that are here, or that are visible a lot here. So here's with decoupled shading. And the key is all those black fireflies essentially go away, because now we have 3 chances to shade any given pixel, not just 1. And so again, this is the same performance as the last image, 2 rays per pixel, 4 milliseconds in total, and it's a great improvement for no cost. All right, so with that, I want to wrap things up here. So in summary, RTXDI is now available. Please go take a look. What we've done is we've seriously tuned the perf number since our prior publication. Now our performance ranges from about 2 to 5 milliseconds. This is on a 3090, but we have the quality knobs to tune this down even further, so you can run it on lower end hardware. This compares to from 20 to 50 milliseconds for the published paper that we had last year. We made some big algorithmic changes, including pre-randomization to reduce incoherency. We moved this incoherency from the inner loop. We reduced the ray count from 5 to 2 at maximal quality, and exposed knobs to reduce this even further. Additionally, we exposed this decoupled shading model, which allows us to decouple the shading from the reuse, giving us better quality at the same performance. Finally, our performance now, scene to scene, is roughly the same. The only real big difference in performance from scene to scene is the cost of the ray tracing. So, for instance, in the Emerald Square, where our total render time took about 5 milliseconds, the reason for that was 3.5 milliseconds was ray tracing time, because we had a lot of alpha-tested triangles. Whereas the other scenes were in the range 2 to 3 milliseconds per frame. And this is a huge performance win over what we had reported previously. All right, so with that, I'm done. Thanks a lot. Please see our developer webpage for more information about RTXDI and for information about getting a hold of it. If you have questions that you weren't able to get answered, please feel free to send me an email or to ping me on Twitter. All right, thank you very much.